Hello, welcome. So this is part 7 of our exploration of Lagrange's theorem. So we successfully proved that indeed if we have some group G that's finite, we proved that indeed if we have some subgroup H of G, right, this is supposed to be G. Okay, let's erase it to write clearly. If we have some subgroup H of G, then we concluded before we're able to prove that the order of H must divide the order of G. But we said that this is not enough. Well, fine, we know that the order of some subgroup must divide the order of the group, but this is still all very theoretical. Ultimately, the only way to truly know something is to observe it. So we need to observe in action. What are some examples of Lagrange's theorem in action? So let's explore that, right? So let's just start with some group and see what Lagrange's theorem is saying. Let's see it happen. So let's consider the symmetric group on 3 elements, S3. Okay, what are the elements of S3? Well, there's the identity permutation, there's the identity that takes 1 to 2, there's the element that takes 1 to 2, there's the element that takes 1 to 3, there's the element that takes 2 to 3, there's the element, so this is supposed to be the symmetric group. So this is the symmetric group. If you don't know the symmetric group, please maybe go look it up online or watch a video on the symmetric group. A guy who's very good at explaining ideas is a guy called Ben Garside. So if you look up Ben Garside, well, he has his group theory videos would have something to do with symmetric groups. So please look that up and then come back and we can continue the exploration. So the symmetric group S3 is given by on the permutation on 3 elements. So there's the identity 1 goes to 2, 1 goes to 3, 2 goes to 3. There is the other one would be, well, 1 goes to 2 and 2 goes to 3. The other one would be 1 goes to 3 and 3 goes to 2. So that's kind of the setup we now have. Well, what's a subgroup of this, right? So this is our group G. Well, if we pick a subgroup of S3, it turns out that, could you think of a subgroup of S3? Is there anything you could see here that's definitely a subgroup? Well, we have a couple, right? So for instance, 1, 2 has order 2, which means that 1 and 1, 2, right, is for example a group. Let's call this subgroup 1, H1. Well, is it actually true that this is a subgroup? Well, okay, it contains all elements of S3, we know that. The other thing is, well, we have the identity, that's good. What about 1, 2? Well, what's 1, 2 times 1? That's just 1, 2. What's 1, 2 squared? Well, 1, 2 squared is 1, 2 times itself, which gives us what? Well, 1 goes to 2, 2 goes to 1. And that means this 1, 2 times 1, 2 gives us the identity. So the order of 1, 2, the order of the element 1, 2 is just 2. Right? Which means that 1, 2 is its own inverse. That's the key. Which means that H sub 1 is going to be a subgroup. H sub 1 is going to be a subgroup, right? Because, well, 1, we have the identity. Every element is inverses in the group. The other thing we have is that, well, it's closed, right? 1 times 1, 2 will give us 1, 2. 1, 2 times 1, 2 will give us 1. 1 times 1 will give us 1. So it's closed under operations, and associativity follows as well, because associativity holds for the group S3 from which this subgroup was picked. Okay, well, question. What's the order of S3? The order of S3 is what? Is, well, 1. How many elements are in S3? Well, we have 6 elements. How many elements are in the subgroup H1? Well, we have 2 elements. Does order of H1 divide order of S3? Well, answer is what? Yes. Order of H1 is 2. 2 divides 6. Right? So we see that if we pick this subgroup H1, Lagrange's theorem is being verified, just with some example. Another thing we notice here is that, look, actually this is also a subgroup. We could think of another subgroup of S3 consisting of the following elements: the identity, the element 1, 2, 3, and the element 1, 3, 2. Well, okay. How do we know this is a subgroup? Well, it has the identity, right? Closure, we need to check closure and inverses. Well, let's see. Is this thing closed? Well, I mean, all we need to check is if 1, 2, 3 times 1, 3, 2 gives us some element that's still in H2. Well, let's check that. 1, 2, 3 times 1, 3, 2. Well, what does that give us? Well, let's see. 1 goes to 3, 3 goes to 1. Okay. Oh, wait. Are we right about this? Right. 1 goes to, right. So 1 goes to 3, 3 goes to 1. Now we have 2. Well, 2 goes to 1, 1 goes to 2, right? So it turns out that 1, 2, 3 times 1, 3, 2 is giving us the identity, right? Which means that, well, 1, 2, which means that 1, 2, 3 inverse equals to 1, 3, 2. Okay, so if that is true, if 1, 2, 3 inverse equals to 1, 3, 2, well, it means we have inverses, right? Because what's the inverse of 1, 3, 2? 1, 2, 3. Okay, inverses exist. Is the group closed? Well, let's see. We know that, I mean, 1 multiplied by any of these elements will give us an element. 1 multiplied by 1, 2, 3 will give us 1, 2, 3. 1 multiplied by 1, 3, 2 will give us 1, 3, 2. Okay, we know that. 1, 2, 3 multiplied by 1, 3, 2, we saw already is going to give us 1, the identity, and the identity in the group. Okay, how about if we multiply elements by themselves? Well, 1 multiplied by itself will still give us 1. What about 1, 2, 3 multiplied by 1, 2, 3? What does that give us? Oh yeah, by the way, the Ben Garside guy for the symmetric group, his video is also on YouTube. So you could look up ideas. If the symmetric group is confusing you, could look up Ben Garside's videos on group theory. He has something on the symmetric group and a couple of other groups. So 1, 2, 3 times 1, 2, 3, well, what's that going to give us? It's just going to be 1. 1 goes to 2, 2 goes to 3, okay. 3 goes to 1, 1 goes to 2, 2, right? And what happens to 2 goes to 3, 3 goes to 1. So we're done here. So we notice that 1, 2, 3 multiplied by 1, 2, 3 gives us 1, 3, 2, something that's still in the group. What about 1, 3, 2 multiplied by 1, 3, 2? 1, 3, 2 multiplied by 1, 3, 2, what does that give us? Well, that just gives us 1. 1 goes to 3, 3 goes to 2, 2 goes to 1, 1 goes to 3, 1, 2, 3. So is 1, 2, 3 in the group? Absolutely. So the group is closed. Okay, this set H2, this subset H2 of S3, this subset, at the moment it's a subset of S3, well, it's closed. Every element has an inverse, right? We have the identity element. Well, it's associative because things were taken from S3 and S3 is associative. Thus we know that actually H2 is a subgroup. H2 is a subgroup of S3. Well, what's the cardinality of S3? We already saw that was 6. What's the cardinality of H2? The cardinality of H2 is what? 3. Does 3 divide 6? Absolutely. Which means that, again, we see again that we observe that the cardinality of H2 does indeed divide the cardinality of S3. Right? And, I mean, pertaining to the other things we noticed, because we saw that in order to prove Lagrange's theorem, we had to study cosets, right? So let's think about the cosets here. For instance, let's say if we start with our, again, if we start with our S3, which was given by 1, 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2, right? So that that was our S3, and H2 we just found that this thing here is a subgroup. Okay. Well, we talked about again our cosets. We talked about the cosets theoretically, right? Let's see what the cosets actually look like. Well, what are the cosets? It means we pick some elements of S3 and multiply them by everything in the group. Okay. So, well, I mean, one coset we know is easy. What's 1 times H2? Well, 1 times H2 is just, right? H2, we get H2 back. We get 1, right? 1, 2, 3, 1, 3, 2. What's 1, 2 times H2? 1, 2 times H2 just gives us 1, 2, right? 1, 2 times the identity. What's 1, 2 times 1, 2, 3? Well, that would give us 1. 1 goes to 2, 2 goes to 1, okay? And then 2, 2 goes to 3, right? And 3 just goes to 3. And then 3, 3 goes to 1, 1 goes to 2. So this is it, right? So if we're to write this well, we now have just 1, 2 times 1, 2, 3 gives us 2, 3. Okay. Let's write that well. Gives us 2, 3 right here. 2, 3. Okay. What about what's 1, 2 multiplied by 1, 3, 2? Well, 1, 2 multiplied by 1, 3, 2 would just give us 1. 1 goes to 3. 1 goes to 3. And what does 3 go to? Well, 3 doesn't go anywhere. 3 goes to 2. What does 2 go to? 2 goes to 1. Okay. And then 2 is just stuck. So that would give us, that would be the coset 1, 2, H2. Okay. What's the coset 1, 3? So the good thing about the symmetric group is that it's, especially this S3, is that it's small. And, well, I mean, there may be a worry that maybe we're spending so much time in calculation, but it's worth the effort. Because otherwise the information is never really burnt into the brain. So, and yet we want to burn it in the brain and we want to observe for sure what's happening, as opposed to just studying some theory that the order of the subgroup must divide the group and that the cosets partition the group, but we've never seen any such partition. Let's actually see one. What's 1, 3 times H2? Well, 1, 3 times 1 would just give us 1, 3, right? That's not a complicated thing. Right, let's, okay. Right, no, actually it's fine, right? I mean, okay, let's write well for once, Make our elementary school teacher happy. 1, 3. 1, 3 times 1, 2. 1, 3 times 1, 2, 3 would give us what? Well, 1. 1 goes to 2. 2 goes nowhere. 2. 2 goes to 3. Where does 3? 3 go to 1. Okay, good. Right. So there we go. And what's 1, 3 times 1, 3 times 1, 3, 2? Well, 1, 3 times 1, 3, 2 is just 1. 1 goes to 3. 3 goes to 1. Okay, fine. So that means that we're just left with 2, 3, right? Because, well, now we'd have 2. 2 goes to 1. 1 goes to 3. So it's just 2, 3 indeed. So we might as well just erase this, right? So we just have 2, 3 now. Right. Okay. So we have 2, 3 right here. Okay. Well, what about 2, 3 multiplied by H2? 2, 3 H2 is just going to give us 2, 3. And then 2, 3 multiplied by 1, 2, 3 would just give us, well, 1. 1 goes to 2, 2 goes to 3. Okay. 3 goes to 1. 3 goes to 1, and 1 just stays there. So we have this. 2, 3 times 1, 3, 2 is just going to give us what? Well, sure. 1. 1 goes to 3. 3 goes to 2. 2. 2 goes to 3. And 3 goes to 2. Wait, so we have 2, 3 multiplied by 1, 3, 2. So yeah, let's see. Yeah, 1 goes to 3, 3 goes to 2, 2 goes to 1. Right, 2 goes to 1 and 1 just goes to 1. Okay. So we really have this, right? Okay. And what about we have just two more elements left. We have the element 1, 2, 3 multiplied by h2. Well, notice something. 1, 2, 3 is an element of h2, right? It's an element of h2. From our study before, we said that if we pick some element of the group that's also in the subgroup, then, like, remember we said before, if we had h subgroup of G, and we pick some little h element of h, then the coset h must equal to h, right? That's what we said. Well, we just picked 1, 2, 3 element of h2, so 1, 2, 3 times h2 should give us h2, but we never actually saw that that is true. So let's verify. Let's observe that. Let's observe that indeed 1, 2, 3 times h2 gives us h2. Well, 1, 2, 3 times 1 is just 1, 2, 3. Okay. 1, 2, 3 times 1, 2, 3, we saw before that that just gives us 1, 3, 2. 1, 2, 3 times 1, 3, 2 is 1 because you saw that 1, 3, 2 was the inverse of 1, 2, 3. So we just have 1. Notice that 1, 2, 3 h2, this coset 1, 2, 3 h2 is exactly the same as the coset h2 is exactly the same as just h2. Right? So indeed, as we expected, if we pick an element of the subgroup, we multiply by h2, well, we get that subgroup back. And so please verify that actually 1, 3, 2 times h2 also does indeed give us our group back. It gives us, maybe not in this order, but it still gives us our subgroup back, right? Because once again 1, 3, 2 is an element of h2. Okay, so we've actually written down all of our cosets, right? There's 6 of them. All right, so, well, how do these cosets partition, right? How do these cosets partition the group S3? So let's observe that. Well, all right, so let's think of this as this is S3. This is our group S3. Just don't want to leave this page because we don't want to keep scrolling down or up for this. Okay, so S3. Well, what was our strategy before? What did we say? How did we say we are going to do the partitioning? The way we said we'd do the partitioning was by getting, well, we pick a coset, right? So for example, we could pick H2. H2 is a coset, okay? So if we pick the coset 1H2, right? Let's write it here. Okay. Well, the coset 1H2, what elements does it have? It has element 1, it has element 1, 2, 3, and it has the element 1, 3, 2, right? Okay. So we're calling that our coset 1H2. That's one partition. Just since 1 times H2 is just the same as H2, we might as well just write the coset H2. Okay. Now the idea was, we'd said before, if one thing we had also observed was that if any of the cosets has something in common with any other coset, then the two cosets are the same. Well, let's look at H2 for instance. Any coset that has an element of H2 in common with H2 equals to H2. So for instance, right? So notice that, for instance, well, any coset that has one in it, right? So let's pick a different color. Any coset that has the identity in it, right? So what cosets here have the identity? Well, 1H2 has the identity. 123H2 has the identity, right? We have the identity here. And 132H2 also has the identity. Now notice that these cosets are exactly the same, right? Because 123 is in the 123 can be found in the coset H2. 123 is also found in the coset 123H2, the one that had 1 as well. And 123 is also found in the other coset. And notice that 132, same with 132. So we are observing again what we did theoretically, that indeed, when we're dealing with cosets, if cosets have one element in common, then they're exactly the same coset. They either have one element in common or no element at all in common, right? So this tells us in particular, using our method, is that we don't need to include the coset 123H2 once you already have the coset 1H2. This means that in the partitions we don't need to think about the partition 1, 2, 3, H2 or the coset 1, 3, 2, H2. So our procedure was, now we look for some other coset that is disjoint from the first coset that we picked to make our partition. Well, we notice that, for example, H2 is disjoint. H2 is disjoint from H1. So, well, why don't we turn that? Why don't we make that our second coset? So now we'd have, well, what are the elements of 1, 2, H2? Well, one of the elements is 1, 2. The other element is 2, 3. And the other element is 1, 3. Right? So this is, we have ourselves the coset 1, 2, 1, 2, 2, 3, and 1, 3. Okay. Notice again that, okay, let's pick a different color now. What are we going to pick? Sure, why not blue? Okay. We notice again, if 1, 2, H2 has, for example, 1, 2, H2 has the element 1, 2 in it. Now let's think of all the cosets that have 1, 2 in them. Well, we notice that 1, 2 is in all the other cosets, right? I mean, 1, 2 is in 1, 3, H2, 1, 2 is in 2, 3, H2. Right? And notice now that since 1, 2 is in 1, 2, H2 and 1, 2 is in 1, 3, H2, 1, 2, H2 and 1, 3, H2 are exactly the same set. Notice that 1, 3 is in 1, 3, H2. 1, 3 is also in 1, 2, H2. 2, 3 is in 1, 3, H2. 2, 3 is also in 1, 2, H2. And the same is true for 2, 3, H2. They have all the elements in common. So really what we're saying is that these cosets, so here we form the coset 1, 2, H2. Right? And notice that these two cosets, H2 and 1, 2, H2, are all the cosets we need in order to get all the elements that are in the different cosets. Right? So all of the blue cosets are really one coset. All the cosets in blue can just be represented by 1, 2, H2. All the cosets in purple, or what's this color? Is it orange? All the color black. Okay, fine. All the cosets in red, we're going to call this red. All the cosets in red are just represented by H2, or 1 times H2. Okay. So it turns out that, okay, so notice, is there an element of S3 that we haven't included here? Well, the S3 has 6 elements. We have all the elements. We have 1, 1, 2, 3, 1, 3, 2, 1, 2, 2, 3, and 1, 3. Right? And there's nothing else. So indeed, we actually included more space than we needed. It turns out that only 2 cosets are necessary. Only 2 cosets are necessary. Only 2 cosets are necessary in order to partition S3. So this is the partition that we've been working with, right? And so I guess a question for you to think about is, in general, if we have a group G, and we pick some finite group, right? G is finite, and we pick some subgroup H of G, okay? How many cosets are there? How many cosets partition? Right, so we can ask a question about these cosets here. The cosets, for example, S3 was partitioned by 2 cosets, H2 and 1, 2, H2, but the number of cosets that partition S3 was 2, right? So usually the way we refer to this is the number of cosets that partition, let's say S3, is called the index of H2 in S3. So the index is written like this: the index of S3, sorry, the index of H in S3, in this case it was H2, the subgroup H2 in S3. This is how it's written. Oh, actually, that's not how it's written. Alright. Okay, so presumably it's written like this, right? This symbol here means the index of H2 in S3, which means that if we get S3 and we partition it using H2, using cosets of H2, how many cosets will we need to partition it? How many distinct cosets will we need to partition it is the question. And in our particular case here, when it came to S3, we needed only 2 cosets. I mean, we had in total 6 cosets, but we only needed 2 cosets in order to partition S3. So here the index of H2 in S3 turns out to just be 2. Okay? And in general, if we have a group G and we pick some subgroup H of G, then the index of H in G is the same thing again. Is if we considered cosets of H formed from G formed from H, how many distinct ones are necessary in order to partition G? That's the index. That's the index of H in G. So, question: what is actually if you want to come up with a formula, what's the formula for the index of G? What does G, index of H in G, actually equal to? What does that equal to? Please do think about that, given that G is finite and H is finite. Okay. So it's probably a good idea for you to look at other subgroups just to make sure we understand this. Um, let's look at some other subgroup, D2N, some other group, sorry, D2N. D2N is a dihedral group. Again, if you're unfamiliar, so the other group we're going to be looking at is, let's look at the dihedral group as another example to actually observe Lagrange's theorem. So the dihedral group, right? Let's look at the dihedral group right here. So the dihedral group is, it's a common group that is used. So if you don't know about it, once again, please do look it up online. The YouTube video is available on the dihedral group, and it's very possible that the same guy again, Ben Garside, really brilliant explainer. Right? Ben Garside very likely has a video on the dihedral group on YouTube, so it may be a good idea to check out Ben Garside's video. Garside, this is a G. Okay. So, anyways, once you've checked out the dihedral group, let's now think about it. The dihedral group D2N, right? Let's work with D6 instead. That's D2 times 3, otherwise known as D6. Okay, sure, D6. But what are the elements of D6? The elements are 1, R squared. Then we have S, the flip, and then we have SR, and we have SR squared. Okay. And we know we are kind of correct because we have 6 elements in this dihedral group. Okay, well, what are possible subgroups of D6? Let's see. Let's think of some subgroup, like, let's say H. We used the H before. Maybe this might lead to confusion. Let's use S. No, we can't use S because we're using S here. Let's use P. Sure, P. P is a subgroup. Okay, well, let's see if we could form a subgroup of D6. Could you think of a subgroup of D6? Well, I mean, one obvious subgroup we have is just 1 and SR. 1 and SR is a subgroup. Why? Because, well, what's all elements of the form SR have order 2. So SR times SR times SR is indeed the identity. Okay, you could check this out, and it comes from the idea that, well, SR times SR is just the same as SR times, let's say, RSR, but RSR in the dihedral group equals to S, so this becomes S times S. And what's S times S? S squared, well, 2 flips is just the identity. So that's kind of how to think about it. But again, these are things, some of the principal identities of the dihedral group. But P is a subgroup of S3. Right. and it's pretty clear, the identity is there, it's closed, etc. Please do verify that P is actually a subgroup of D6. Having verified that, observe that the order of P does indeed divide the order of D6. And it does, doesn't it? What's the order of P? 2. What's the order of D6? Haha, 6. What's 2 divided by 6? Well, some natural number, otherwise known as 3. So indeed, right, again, we are observing that Lagrange's theorem actually holds. Right? The order of every subgroup must divide the order of the group. And we could think about cosets if we like. Yeah, why not? Why not? Why not? Let's well, maybe we're not going to look at all the cosets that partition it. Well, it is pretty small. Yeah, maybe not. Okay. So I guess let's do this instead. See if try conducting a study of D6. Right, so D6 we said was the same as just 1 R squared S SR squared. This was D6. And our P we chose to be, well, we just chose P to be the subgroup 1 and SR. Okay. So here's a task for you to try out. See if you can, one, figure out all the cosets. So write down all possible cosets, right, of D6 formed by P. That is, i.e., all GP, all cosets GP, where obviously G is an element of D6. Okay. So first write down all possible cosets. Try that, and then next thing to do is see if you can figure out which ones of them are the same, which ones are not the same, and then try and create the partition. Actually, to is just create a partition. Create a partition of D6 using P, using the subgroup P, and maybe the next task is observe that the index of P in D6 actually happens to be 3. That is, you need only 3 cosets to partition D6 correctly, in such a way that, well, every element is in some coset, the cosets are pairwise disjoint, and the partitions are just cosets. Okay, observe that D6, the index of P in D6 actually equals to 3. Alright, so we are now not just theoretical people. We actually we've now observed, right? And this is core. This is like something that's not emphasized enough, but just merely knowing something theoretically in terms of symbols is not enough. It's important to actually see how things work. So now that we've observed Lagrange's theorem in action, we have a better understanding of it. The next step is going to be to actually think about, well, okay, fine, it's all well and good, we've seen Lagrange's theorem in action, but still, some interesting observations, but what is it good for? So we're going to look next at the consequences. What are the consequences? What are the consequences of Lagrange's theorem? What are the consequences of Lagrange's theorem? Please think about those. See if you could figure out why saying that the order of every subgroup must divide the order of the group is so useful. Why is this useful? Why is the fact that order of the subgroup divides the order of the group so useful? Why is it so useful? Right. So thank you very much for watching this video, and hope to see you in the next video. Otherwise, have a relentless week. Bye.